And the next speaker that I have the pleasure of introducing is Greg Stevens. Greg is at the RU Amsterdam, and he'll start the day off with a pedagogical lecture, followed by a talk later.
Okay, everything working? You can hear me? I think I can hear me. So, good morning. Thank you for everyone for coming, for the organizers for inviting. I want to get a sense of who, I've met some of you, I've met a lot of the organizers and the faculty, but I want to get a sense of you back there. I've met some of you. Okay, so yes, you. How many people are physics? Basically everyone? There's no, and how many people are not physics? Okay, for those of you who are not physics, how do you identify? Just shout it out. I'll sit here, yeah. Biology, great. Who else? Same, biology? How many people biology? Okay, how many people did that, do those two categories not capture? Okay, for the non-captured people, how do you identify?
Mostly biology, a little bit of physical.
Okay. Engineering, okay, great. So my goal today is to start on the board to lull you into a sense of complacency that everything will go very slow and you can ask questions, and then I will hit you with 1,000 slides describing every detail of my work. Not really, okay? So, but I want you to jump in and ask questions. I will probably ask questions of you because we want to make sure that the concepts that underlie the research that we do kind of get into your heads in one way or another. It's a varied background, so some of you may know some of the things that I'm talking about, some of you may not. That's all fine, okay? And let's see, I think the idea we're thinking about living systems. This is a bio course, but we'll just generalize that a little bit because there's some things that we might also think about that aren't living, although mostly it's living. I also want to see, is that big enough so that you guys can see when I'm not in the way? Okay. Okay. So we're gonna. I think about, as a researcher, I think a lot about behavior. So how does an entire organism organize itself to do things, right? This is the place where evolution matters. It's the place where you reproduce or get eaten. So it's a really interesting scale. It's very dynamic, right? How you move around the world is obviously very dynamic. And it's remarkably complicated, even for single-cell organisms. And so we're going to have to come up with language that helps us describe what we see and ultimately sort of allows us to understand why we see what we see. And when you think about even biophysics more generally, there's sort of two big, I don't know, traditions. So you might start with statistical physics, which was really successful at understanding thermodynamics, is broadly influential, not just in those systems, but in our information systems. Okay? And maybe a really common system that you might think about for statistics, or sorry, statistical physics would be some sort of Ising model. Okay, so let's see. Do those words familiar to some? Okay, all right. And we know that there's a lot of interesting things in these models. There's a lot of interesting approaches. This is a remarkable success in the physics of complex systems, right? So the ability to explain the macroscopic behavior of the gas particles in this room from its microscopic interactions, or to explain the macroscopic behavior of a magnet from its microscopic interactions. But of course, I'm sorry, if it bugs you that I go across, I think we're going to have to go across the. Yeah, bugs me. You know, there's a related. We already heard a little bit about these things. And so there's let's see, there's sort of statistical physics, dynamical systems. Of course, these are totally related to each other, right? So underneath, I don't know, how many people remember from their statistical physics that we introduced something called, you know, the Boltzmann ensemble or the Boltzmann distribution, right? Show me your hands, wake up. Excellent. This is the biggest trick in undergraduate teaching. We take this crazy, kind of chaotic, high-dimensional dynamical system of gas particles interacting with each other, and we just tell you that I can replace all of that with a measure. And we don't often sort of probe you or probe ourselves as to why that's a good idea, right? But it does work, and that's the origins, that's the foundations of statistical physics. So deep inside, dynamical systems, even chaotic dynamical systems and statistical approaches are intimately related. But somehow we often tend to go one way or the other. And, you know, so these arrows really go both ways, and especially when we think of living complex systems. We're going to want to have all these tools in our toolkit. Right? Sometimes we might think that this is a more relevant approach. Sometimes we might think that this is a more relevant approach. And interestingly, in India, actually, from what I read, I see more dynamical systems than I do outside of India. So that's really interesting. You guys are already advanced relative to the rest of biophysics. Okay? And maybe an example. Here's the Ising model as an example for statistical physics. Has anybody seen this kind of equation before? This is the logistic map. So it's a dynamical system. It's a discrete time dynamical system. How many people have seen this before? Oh, a lot of you. Okay, so you've done this, right? So it's a discrete time dynamical system. You can vary. It has it's a one-dimensional system given by x. So, and you can, x is between 0 and 1. And it has this really interesting behavior as a function of this parameter r. So if I plot, let's say, the end point of a long trajectory. So let's say x at t equals infinity. All right? And I look at where that is, then let's see, 1, 2, 3, 4. And that behavior, you've seen this maybe. It's called a bifurcation diagram. Oh, that goes all the way to 3. And you get more bifurcations, and then over here you get chaos. So just, you've seen this before maybe, you've looked it up on Wikipedia. So the idea is I simulate this dynamics for some value of r for a long time, and I just plot what that point is, where that point is between 0 and 1. And between r equals 0 and 1, there's a fixed point at 0. From 1 to 3, there's a fixed point, stable fixed point that's here. And then you get cycles, and then over here you get chaos. Really simple system, but it has great lessons, just like the Ising model is a simple system and has great lessons, okay? The lessons here, well, let me ask you. So how should we quantify the complexity of the dynamics that we see? So is the part of the bifurcation diagram with where you approach a fixed point, is that more complex than a cycle? Is a cycle less complex than chaos? What do you think? How should we characterize the complexity of the dynamics that we see? What do you think? Yeah.
The number of points that you can visit, or you could possibly be at the end of, I think infinity. So like for one fixed point, that'll be less complex than two fixed points. And so for limit cycles, it's higher, but then it can be higher.
Okay. Okay, that's one possibility. So in some sense, the period of the attractor, where this is like a period 0 attractor, and then you go to a period 1 or a period 2. Okay, and then maybe we could describe, somehow in that same language, we could describe the chaos, and that's fine. Okay? Let's see. So there's a couple of things I want you to remember. So typically, even in this simple map, what happens at early times is not something that we can easily discuss universally. So early time dynamics isn't universal. This is going to be important for what we do today. So that's why to plot, this is a bifurcation diagram. You could have asked me, why am I only plotting, the endpoint of a long trajectory? You could also ask me, does it matter? I mean, I could start with different initial conditions and maybe I get different endpoints. That's a good question. But the reason that we plot this at long times is because we think what happens in this kind of dissipative dynamical system is you settle into one of these attractors. And how you settle isn't as universal as what you've settled onto. Okay, so we look at long times. Okay. And so he was suggesting that we count the number of periods. That's one possibility. Since you already heard about this thing called a Lyapunov exponent, and generally, especially in this case, you can think about it in the following way. So I have a trajectory. I have two trajectories. Oh. Okay. And I start two trajectories close together in this map from their initial conditions. They will deviate from each other generally, right? Or they might. And that deviation can grow exponentially. And that's our exponent. Okay, so this is delta t. Okay. So that might be another way to characterize the complexity of this map. And let's see, so just for background, for an n-dimensional dynamical system, there are m exponents. So let's say lambda 1, lambda 2, lambda m. And if lambda max is greater than 0, then you have chaos. Okay, we're in a one-dimensional system, which I can do on the board, which is why, but in general, you could have a 2, 3 high-dimensional system, and there are as many of these ways of changing the distance between your nearby trajectories as there are dimensions in your phase space. Basically, you can think about along each one of those dimensions. So there are m of these exponents. If any of them are positive, then the system is chaotic. There can be more than one that's positive, right? Yeah.
Your bracket, x of t naught plus delta naught should have been after t naught.
Oh, I do that all the time. Yeah? Good. And there's going to be a million things like that. Jump in and fix this. Okay? And if you have a general map, one-dimensional system, discrete time map, then there's one exponent, because there's only one dimension, m is equal to 1. Right? And that exponent, let's call it okay. So in m dimensions, this is a harder calculation. In one dimensions, if you know so that essentially this f prime, df dx, the absolute value of f prime, is essentially the one-dimensional Jacobian. You're taking the absolute value of the one-dimensional Jacobian. There's a logarithmic transformation which comes from the fact that this lambda is measuring this exponential divergence. That's your exponent. And if we go back here, then the chaotic transition for the logistic map is 3.56 something here. So from here to here, lambda is less than 0. And when it's not always chaotic above here, but in this region where there is chaos, then lambda will grow beyond 0. Okay? You also heard, so from the lectures, the lectures from this week, Monday and Tuesday, you heard about entropy rate, I think from William. What's that? Sorry, I can't hear. With lambda, no. No, good point, right? So it doesn't tell you, all that tells you is the stability, right? You could have a stable cycle. If it's stable, then the lambda is negative, but that could have been a fixed point, that could have been a cycle. No. Yeah? Okay. And William mentioned this just in passing. Even though this is a deterministic dynamical system, so there's no noise, there is a notion of entropy rate, and now we'll try to understand that entropy rate. And that entropy rate is formally the sum of the positive exponents. So if there are no positive exponents, so here, h is 0, the entropy rate is 0. If there are positive exponents, the entropy rate is non-zero. Okay, and it can vary in its magnitude, yeah. Yeah, that's a really good question. And so I think that's kind of the goal of my lecture today. So why don't we go through the whole thing and then come back. This is, I think this is Pessin's theorem for dynamical systems. Doesn't matter. And so I'll tell you the origin, though. So it's not obvious, because you usually think about entropy coming from probability distributions, coming from things you don't know, right? And from noise or from random stuff. So the origin of this came from Kolmogorov. And the idea was, how could I find some quantity that distinguished not just whether I'm chaotic or not chaotic, and that's done by, that could already be done by the positive Lyapunov exponent, but by how chaotic it actually is. And so this is actually formally the Kolmogorov-Sinai entropy rate. It comes from dynamical systems. What we will show today is you can think of that as a Shannon entropy rate. And so you really can think about it in an information theoretic sense. And it's just to motivate this important quantity of the Shannon entropy rate. Okay, so we'll come back to your question at the end, but our goal is to understand H. And I don't mean H, so this is entropy rate H. I don't mean H specific to dynamical systems. We're going to use these as an example, but I mean entropy rate as a concept. How many people have come across entropy rate as a measure of complexity in some way or another? Excellent, my perfect crowd. Okay, good. Okay, so that's what we're going to do today. Okay. Any questions? Right, so I'm not saying that there aren't other ways to classify the complexity of this time series. We'll come back and talk about why this is a good thing to do. Okay, so let's. So now we're going to make a big leap here. And we're going to forget about our dynamical systems. They'll come back at the very end. Okay. I want to make sure that we're all on the same, we all have the same fundamentals for understanding the objects that we're going to be talking about. Okay, so this is Shannon entropy, and we're going through the basics. We're going to keep all of our variables discrete. That's a lot easier. So we're going to say that that's some random discrete variables. There are, let's say, m of them. Okay, with m outcomes. And with those outcomes are, okay, associated probabilities. Yeah, of course. That all has to sum to 1. These are all positive, semi-definite. And what is the formula for the entropy? You know this. This, I think, I'm pretty sure you know. What's the entropy if I give you P of this random variable? I don't hear you. Shout it out. Minus some pi, well, I'll put it on the board, pi log pi. Yeah. So you can write this, what am I using? I'm using x, so I'm using S for entropy. I will use S for entropy and H for entropy rate. I'm sorry, that's a little weird. Minus sum. Is that what you said? Is that right? Okay. And this has some properties. So this is always positive. Why is it always positive? P is always positive. Log P is always negative because P is less than 1, so the negative sign takes care of that. Okay, so P is always positive. What kind of distribution maximizes the entropy of this single variable? Uniform? You agree? You're going to go with him? Okay. Lucky. Okay. So it's max for uniform distribution. what kind of distribution minimizes the entropy? Pardon? Delta. So if all the p's but 1 are 0, essentially if you have a deterministic outcome, there's no entropy, right? So also for deterministic outcome, right? So I should say s equals 0. Okay. We'll come back to, there's another property that I want to put down, but we'll come back to it because additive for independent variables, but we're talking about just one variable. Okay, but what is it? So let's put, oh, I didn't say something. What are the units of entropy? What? It's bits? Oh, she says bits. Does anybody disagree? You're going to go with her? No. What are the units of entropy? You're right, but you're also not completely right. Yeah, so it all depends on the base of your logarithm. So if for one reason or another, and in dynamical systems, they generally use natural logarithms, you have nats. Bits, nats, you could dex, there's other things. It just depends. We add the unit so that we know what logarithm you use to define entropy. Okay? Bits is a fine answer, but there's others. So let's measure in bits. So let's do a biased coin, just to make sure you're all on the same page. So let's bias a coin so that it comes up heads with alpha and tails with 1 minus alpha. And let's measure the entropy as a function of alpha from 0 to 1. Okay, so you said that if alpha is 0, so it's a totally biased coin that it comes up heads, the entropy is 0. We already did that one. If you bias it the other way, so it always comes up tails, I said heads before, the other way, that's also 0. You said it was maximum here at when it's totally equal, and so I could draw this with something like that. Right? What the entropy of a biased coin looks like. Now, what is entropy, though? Okay, let's see if we can make average. He says it's the average surprise when you're getting outcome. Let's see if we can make that a little more, we can internalize a little bit, okay? So suppose, I'm just going to write it this way. You have a 10-sided die. You know, if you play Dungeons and Dragons or something, you have one of these crazy dies, comes up with 10 sides. The entropy of a 10-sided die is 3.32 bits. Right? And what is that? That's log 10. Yep. But what if my die was 100? Or even 1,000? Really crazy. That's a crazy die. All right, what is that? 9.96. Okay. So that you know, that was part of this. Now, how would I understand his question? Have you ever played 20 questions or some version of this? So suppose that someone in the room rolls one of these die, like the 10-sided die, and they get an answer, but they don't tell you. You're only allowed to ask yes, no questions of what the outcome of that die was. And I ask, and you all do it, and we do this many times, how many questions do you need to ask? What's the minimum average number of questions you need to ask? It turns out to be this, which is actually why 20 questions works at all. Kind of crazy, right? Or 10 questions, or sorry, you know what I mean. That you only need 3, you know, on average, you need this many bits, this many yes or no questions. We could do the exercise if we had time. What's remarkable is that that only grows linearly with the complexity of your die. So I give you 10 times more options. You just have to add, roughly speaking, double the number of questions, which is why you can really sort of hone it down. And that's really what entropy is. Sort of the number, how many questions you need, the minimum number of questions you need to be fully certain of the outcome. Okay. There's another interesting example, maybe less common. So after Shannon developed this pretty readable paper on the universal theory of communication, only a few years after that, he wrote a really amazing paper on language. You know this paper? I'll give it to you. It's great. So 1951. So this is Shannon, 1951. And essentially, we have a really interesting die in the world that we could play around with already, right? And that die is the way we write. I'm going to do this in English, but you can do this with any other language, right? The answers will differ because the information content of the symbols is different. So if in English, you could imagine you have an alphabet. So A, B, C, D, E, all the way to Z. And let's see, the probability for A is maybe pretty high. E is also going to be, let's see, E is higher than A, right? Maybe there's not as many C's. It's going to look something like this, right? And then, Z, not many Z's. That's a I should say maybe dice. I don't know. Probably should say die, but I'll say dice. So and where did these probabilities come from? So we sample these probabilities. Right? So you could take your favorite book, you could take your favorite author, you could take your favorite corpus, which includes many authors, many books, and you could just ask, how often do I see an A? How often do I see a B? How often do I see a C? And so on. Okay? Yeah. And there's already interesting information in this really simple distribution. So I did this a long time ago for Jane Austen, multiple books. I don't know. It was easy to find. You can find her text on the internet, and she writes fairly without a lot of crazy words like Moby Dick. And so that was a nice one. If you do that, then something like that, the entropy turns out to be 4.2 bits roughly. Why is that interesting? So S uniform is 4 log 22, log 26. Okay. So already, even in this really simple example, where we haven't really touched grammar, we have no rules about, all we're thinking about is the relative probabilities of this 26-sided die, which is what we write English text with. And those probabilities are unequal. That unequal probabilities is measured by the reduction in entropy from the uniform distribution. Okay? Fairly basic, but also interesting because you get a sense of these are interesting things that you can measure directly, and it already has some meaning. We don't use, and this is true in any language, you never use the symbols of the language are not used uniformly and equally. You could ask why, and that's a really interesting question. I don't think I have an easy answer to that, but they're not, and that's the only point that we need today. Okay. Okay. So another thing to point out, and then we're going to go to multiple variables, is that mostly, not entirely, but really entropy really comes into its own when you start having more than one variable and you start doing comparisons. already you can see that, we have an answer for this number, 4.2 bits. That's the number, the average number, minimum average number of questions we need to guess which letter we're looking at. And that's, but we get information about sort of how non-uniform the distribution is by comparing this number to this uniform. So we'll come back to this. Let's see, let's go, just say it here. Okay, so let's write down, now I'm going to use sigma. So let's just do two. Two variables, discrete, and what's the entropy? Well, it's exactly what you said before. The only thing is that our right? That's the entropy for this two variable distribution. All right? Now, do you know what it means to be statistically independent? How would if sigma 1 and sigma 2 are statistically independent, what does that mean for the joint distribution? So I have a general joint distribution for these variables. These variables may or may not interact, but there's a unique form for the distribution if the variables are independent. What's that form? Sorry? Product. So this joint distribution is the product of its marginals. So if and only if the variables are statistically independent. And that's a measure of independence that's not related to any form of the distribution. It's general. It's not about correlation or decorrelated. It's true in general. Right? This is the measure of independence. What does that mean for what does that mean for the entropy? Well, so this becomes P sigma 1 now I have log of P sigma 1, and I'm going to already factorize because this is a product, so that becomes an additive. So I have this. Right? So this is for independence. On this side, you can see that there's no sigma 2, so I can sum over sigma, so sorry, there's no sigma 2, so I can sum over that, that's just 1. So this term becomes, right? And this term you've seen this before? How many people have seen this before? Oh, not everyone. Okay. Let's pause for a second. Does that make sense? So if you take that this is what independence means for statistics, then, and we already know the formula for the entropy, then this is just true. That is, when the variables are independent, the entropies add. Okay? And that really would have been one of the other things that I would have put under here, but it's better to do it this way. Yeah? Yeah? let's see. So let's do one more over here. So that suggests a really nice picture. See if I can do it. Ooh, that's okay. So let's imagine that this circle, the left circle, is the entropy of sigma 1. This guy, sorry, maybe I'll do it up there. No, let's see, let's do it down here. Okay, the entropy of both of them together is the area of those two circles. And then the difference, sorry, how much those circles overlap. So because we said that entropies add when they're independent, the natural measure of how much they're independent is essentially, it's exactly the difference between independent yeah. That's mutual information, right? So because we have a very natural measure of independence, the entropies add, we have a natural measure of, if we subtract the independent entropy from the joint entropy, that's the amount of information that one variable tells me about another. Okay, and let's do a little more. So this one is sort of the entropy of 1, but conditioned on 2. Entropy of 2 conditioned on 1, just the part, the eclipsed circle. Okay. So let me remind you, let's say here, this is a reminder about conditional probabilities. You guys seen this formula before? The joint distribution can be written as this conditional distribution times the probability of the conditional variable. Okay, so that means that we can write yeah.
In the diagram for S up there, shouldn't sigma 1 and sigma 2 just be in the I region?
What's that?
So we've got circles, right? So you're saying S of sigma 1 given sigma 2, shouldn't that be inside the overlaps if that's where it's sort of outside? Because if you're saying it's given sigma 2, it should overlap with the region that you're denoting as sigma 2, unless I'm like interpreting how you're writing it right.
Let me think of that for a second. Yes, I think so. Let me finish this and then come back to that. Yep. Remember that so that we can write S of sigma 1, sigma 2, the entropy of the joint distribution is equal to the conditional entropy. Okay. So that means, let me go up here, that I can think of multiple formulas for I. So here's one. Okay, so here's one. Okay. So just by focusing on different distributions, I could write the information as the difference between the full entropy, the difference between the independent entropy and the joint entropy. But I can also think about that as the difference. So I have the entropy of S1, which is this whole circle. How much is that reduced by this, and that's this. Simultaneously, but there's no difference between, it's symmetric between S2 and S1, so I can think about, I have this full entropy of S2 in this circle, but it's reduced by this conditional entropy, and that's this amount, Okay? So notice also that this is symmetric in sigma 1 and sigma 2. Okay. So let's put some properties. So I is always greater than or equal to 0. Okay. So let's think about what this means for the circle. So when these two variables are independent, the circles don't intersect, right? So that's the case where the total entropy is the sum of the individual entropies. That only happens when the variables are independent. So the circles that I would write if the variables are independent are disjoint, but they don't overlap. How would I write the circles if so that it achieves its maximum value, one of its maximum values? Give me an example of drawing the circle. What's that? Yeah, so I would put one circle inside another. I didn't have to draw these with the same size, right? So that's the most information you can have, either one inside the other. Yeah, one inside the other. And perhaps, well, they're all equally important properties, but a really important property, and unlike other measures that you have in statistics, is that this measure of information is invariant to a large class of functions. So as long as those functions are invertible, you get the same information, which is unlike, for example, linear correlation. Okay, and so that invariance is one very important reason why we use information in complex systems, where there's no reason, for example, to believe that the variables that we have access to in measurement or anything, are linear, that we can have a linear model or some well-defined. Sometimes we don't even know the model. Okay, so what's really interesting, you pay a price. We'll talk about the price that you pay later. But by using information, you're measuring these dependencies for this whole class of functions, f and g, right? And that's the power. Okay, how am I doing on time? 5. Let's pause for a moment. Questions? That's really basic Shannon information theory, mutual information for 2 variables. Let me pause and see if there's questions on these variables. Yeah. No, the shaded region is I. So the shaded region is I. No, you're fixing sigma 2. That's what a conditional means. That's why. Yeah, that's what a conditional means. You're fixing sigma 2, and so you still have, when you fix sigma 2, you still have this much variability in sigma 1. That's why it's that circle. Okay? Good question. Other questions? Have you seen this before? How many people have seen this before? Few, but how many people have not seen this before? Okay, good. Okay, so we're kind of running through Shannon information theory step by step. And I just want to emphasize a little bit, because now we're going to go to bigger variables. You see, we started with 1 variable, and already we learned a little bit. By 2 variables, and again, you see that what we're doing by 2 variables, we have this new concept, mutual information, and that mutual information is this comparison of entropies. You could compare the independent to the joint or to the full. You could compare the individual to the conditional, but it's a comparison of entropies, right? And it's that comparison where we really gain information. Okay, we also, of course, we measure mutual information in the same units that we measure entropy. Okay, let's do, let me go all the way back. How's the size? You can see in the back, everybody's okay? All right. Let's go back here. So now we're going to go, I think, where it gets even more interesting, or at least where we get closer to our goal of, remember, our goal was to understand H. Let's go back. Okay, so the numbers are going to be a little bit different because I changed slightly how I sampled. I'll tell you about that in a minute. Okay, so sorry, let's do it here. Okay, so let's go back to our example from Shannon. I said if you sampled 1 letter, then you got an entropy of about 4.2. What happened here is that I increased the alphabet from 26 to 27, so I could include a space, and I'll tell you why in a minute. Okay, so that's the 1-letter entropy. What do you think the 2-letter entropy is? So these are 26 letters plus 1 space. I don't think that really matters. What do you think the entropy, so now that's my random variable here is a 27-sided die that's unequal. My random variable for 2 letters is what? How big a die do I have for 2 letters? So this is a 27 squared die. Okay, and what do you think happens to the entropy? So let's say that the letters were independent. If I wrote text in a way that all the letters were independent, so I'm talking about 2-letter sequences. So sorry, maybe that's not clear. So I'm talking about sort of these n-letter sequences. N will be small for us at the moment. If the letters were independent, what would the 2-letter entropy be? Quick, or you don't get coffee. That's the 1-letter entropy. What would the 2-letter entropy be? What's that? Twice. That's right? That's the point. If they're independent, the entropies add. And then, okay? So if it were independent, it would be here, and it would be, so as independent for 2 letters, I'll stop, we'll take a break in a minute, but we're gonna come back and stay on the board, would be, 8.2. What do you think the actual answer is? Higher or lower? He's made it easy for you. Now you just have to raise your hand for higher. Higher than 5 or 6? Lower than 5 or 6? Oh, you speak in very boring ways. Okay. It's higher. So 2-letter entropy here is 7.4. Again, you could sample this yourself. So they're still pretty weakly interacting. 2 letters, okay, it's less than 8.2, but not by a lot. Right? And that trend continues. But for 3 letters, it's down by even more. So 3 letters turns out to be 9.9. Okay, so you see what's happening, right? As I increase my die, in principle, I should be multiplying my entropy by the factor that I'm increasing. So this could, in principle, double, in principle, triple, but that doesn't happen. So why is it that the entropy of 2-letter sequences is smaller than twice the entropy of 1-letter sequences? How would you describe that observation? What does that mean about the letters? What's that? Some combinations are more favorable than others. The letters are interacting, right? They're statistically interacting, absolutely. Right? Okay, so let's see. How about I just want to introduce the entropy rate for this simple example, and then we'll take our break, okay? So I'm just going to do the same data. Because the entropy naturally increases as you increase the number of sides on your dice, right? So it's hard to really compare. I mean, we can do it, but it's a little easier if we talk about sort of the S per letter. Because the length of our sequence, because that will modulate this increase. And so for 1-letter words, it doesn't matter. Oh, sorry. 4.1 bits. But for 2 letters, so now I'm taking the entropy, let's see, this is my 2-letter entropy, and I'm dividing by 2. Right? Because there's 2 letters. So that divided by 2 is 3.7. And this divided by, that divided by 3, 3.3. Okay. So the entropy of these larger and larger die is growing, but part of that growth is just the number of possibilities of the space, right? This is a 27 squared space. That's a 27 cubed space. To account for that growth in the space, we divide by the length of the space, and still the entropy per letter is decreasing. Another way of saying that is that even, it's kind of obvious, with 3-letter sequences, the letters are still interacting with each other. You could imagine that if they get really far away, then maybe the letters stop interacting, and that's where we'll pick up after the break. Okay, but this is our Our first, what we're getting to here is the early version of what will be the entropy rate. Okay, so let me pause here for our break, but first ask if there's any questions. Yeah. Sorry? How about I rephrase the question? How far do I have to go before you think you don't see this entropy rate decrease for language? Give me a guess. What's that? Length of a phrase. Good, short, possibly, certainly we know that, but think about like a detective novel where you introduce the character in the first chapter and only find out that that guy did the murder in the last chapter. Crazy, right? So there's meaning, there's correlations in text is one of the hardest signals because there's correlations in text that actually extend super far. So to really measure this infinite length entropy rate in language is a really interesting challenge. Shannon had an answer to that challenge. In some sense, the chatbots figured out an answer to the challenge, although not a principled one. So they just figured out some way that they would sort of sample these long sequences. It's not clear that that's not the full way that you could sample them, and that's why they can go really far back, and that's part of where their power really lies. Okay? Yeah. Okay, let's take a coffee break and then see you back.